welcome to Easy BTech, your guide for BTech and beyond. And we are discussing about subject signals and systems. And today's session, properties of Laplace transform, very important session. Already we discussed the properties, again still we have properties. And before going to discuss properties of Laplace transform, all of you subscribe, share the channel. This channel is very helpful to you. Let's start our session, properties of Laplace transform. So in the previous session we discussed some of the properties. Let's have remaining properties in this session. So first we are going to discuss differentiation in S domain. Differentiation in S domain. Differentiation in S domain. In the S domain. So let's see what is the differentiation in S domain. So first we see statement. The statement is saying that if x of t Laplace transform is x of t Laplace transform is x of s, its Laplace transform is x of s, capital X of s, then differentiation in S domain. Differentiation in S domain means d by ds of x of s. This is the differentiation in S domain. So it will be minus t into x of t. So in time domain, x of t is multiplied by minus t. If you differentiate x of s one time with respect to s. See the proof. So first we take Laplace formula. Laplace transform of x of t is equal to x of s and is equal to integral minus infinite plus infinite x of t e to the power minus st dt. So this is the Laplace transform. Now we are going to differentiate x of s with respect to s. That means d by ds of x of s. d by ds of x of s is equal to d by ds of this total integral minus infinite plus infinite x of t e to the power minus st dt. Okay, e to the power minus st dt. So here we have integration and differentiation, but integration is here with respect to t, differentiation is with respect to s. Therefore, they are not cancelled because they are not in same domain. So now this we can write as integral minus infinite plus infinite x of t into d by ds of e power minus st dt. So we are seeing s term that is available in e power minus. Therefore, differentiation is applicable to this e power minus st. Right? So now perform the differentiation. Integral minus infinite plus infinite x of t. What is the d by ds of e power minus st? E power minus st into minus t dt. Okay. Right? Now this integral I am writing as in the next step is equal to integral minus infinite plus infinite minus infinite plus infinite minus t x of t into e power minus t dt. E power minus t dt. So if you observe this integral, it is like Laplace transform formula. So here only x of t, that is why Laplace of x of t. But here minus t into x of t, this total will become Laplace transform of minus t x of t. Right or not? So in the place of x of t, we have minus t x of t. Therefore, it is Laplace transform of minus t x of t. So right side we have Laplace transform of minus t x of t, and LHS we have d by ds of x of s. right? So finally we can say that Laplace transform of minus t x of t is d by ds of x of s, d by ds of x of s. Okay, d by ds of x of s. For example, if you perform another second time differentiation of x of s, second time differentiation of x of s, then what happens? That is again d by ds of x of s. So what happens left side? Minus t into x of t. Again this total is multiplied by minus t again. This total is multiplied by minus t. If you simplify, it will be minus into minus plus t square x of t dt. Sorry, x of t. Its Laplace transform will become d square ds square x of s. Right? So this is the clarity. Okay. This is the property differentiation in S domain. Right? Now we move to another property, initial value theorem. Initial value theorem. Initial value theorem. So what this theorem is saying, we discuss now. So here x of t is 0 for t less than 0. Means x of t is a causal signal. This is causal. X of t is a causal function. Then or causal signal. Then what is initial value is x of 0 is equal to, or we can write x of 0 as limit t tends to 0 x of t. Initial value of the signal, or the value of the signal t is equal to 0. Starting value of the signal, that is x of 0. So we can get this x of 0 value limit s tends to infinity s into x of s. So its Laplace transform is multiplied by s, then limit s tends to infinity. Then we can get the initial value of the signal. That is the meaning here. But the signal is causal. X of t is 0 for t less than 0. So to prove this property, or to see this proof, we consider time differentiation property. With the help of that, we can do it. So we know that property, time differentiation property, we know that as per time differentiation property, Laplace transform of d by dt of x of t. This we know. Laplace transform of d by dt of x of t. In case of causal signal. In case of causal signal. So what is the answer? S into x of s minus small x 0. Here initial value x0 means initial value of the signal, or value of the signal at t is equal to 0. Right? So this is the initial value. So this already we know. So we are writing it. We are taking it. Then we know that Laplace formula, general Laplace formula, Laplace transform of a signal x of t. How to write it? Integral minus infinite plus infinite x of t e to the power minus st dt. Suppose here x of t is 0 for t less than 0. Therefore here 0 to infinite, not minus infinite plus infinite, because 0 x of t is 0 for t less than 0. E power minus st dt, right? Then we are going to write this one, LHS, Laplace transform of d by dt of x of t. Laplace transform of d by dt of x of t. So how to express, how to write it? So same way, integral 0 to infinite, here d by dt of x of t e to the power minus st dt. As per Laplace formula we are following or we are writing. Now consider this e power minus t st is u and this d by dt of x of t is v, uv. So I am going to expand uv. So what is uv? Integral uv, u integral v minus integral u dash integral v. So this I am going to write now. So this is equal to u means e power minus st. Integral v, integration of d by dt of x of t is x of t, right? Minus here. Okay, so after taking uv, this is not required. uv expansion is not required. Just leave it. Just write Laplace transform of d by dt of x of t. So this no need of uv expansion here because we can get the solution. We can have the answer. So here LHS left side we have Laplace transform of d by dt of x of t. So that we know that s into x of s minus x of 0. That I am taking s into x of s minus x of 0. Right? So is equal to right side we have 0 to infinite d by dt of x of t into e to the power minus st dt. Okay. Now, if you see in initial value theorem, x of 0 is equal to limit s tends to infinity s into x of s. So, what I am going to do, both sides apply limit s tends to infinity. That is the step required. No need of uv here. So, both sides, on both sides, limit s tends to infinity. We are taking. Okay. This we are going to take limit s tends to infinity. Both sides we are going to take that limit s tends to infinity. Then we can see, so here left side limit s tends to infinity. So what we have, s into x of s minus small x 0, and right side also limit s tends to infinity. So what we have here, integral minus 0 to infinity, integral 0 to infinity, dy dt of x of t e power minus st dt. So by applying limit s tends to infinity, this e power minus g infinite, what is e power minus infinite, is equal to 0. So this total right side term will become 0, right? Because e power minus infinity is 0, right or not? Then this one, so in left side limit s tends to infinite s into x of s minus x of 0. So this x of 0, this limit is not applicable because there is no s term. So by this we can tell now x of 0 is equal to, what is x of 0? Limit s tends to infinite s into x of s. This is the proof. Simple, very simple. Okay, this is the proof. So this is the initial value. So what is initial value theorem saying? To find the initial value of the signal. What is this initial value of the signal? So this initial value of the signal we can do in this or using this limit s tends to infinite s into x of s. Initial value of the signal. And similarly we have final value theorem. That also we can discuss now. So final value theorem now. Final value theorem. So what is the final value theorem? See the definition. Same here also x of t is 0 for t less than 0 means causal signal. X of t is a right-sided or causal signal. Then the final value of the signal means x of infinity. X of infinity can be written as limit t tends to infinite x of t. Final value of the signal. This can be obtained by doing limit s tends to 0 s into x of s. So x of s means Laplace transform of x of t multiplied by s, then substitute s is 0. Then you get the final value. That is the meaning here. See the proof. So proof is done with the help of differentiation property. Same initial value theorem, final value theorem. Proof is done with the help of differentiation property. So we know that differentiation property. We know that Laplace transform of d by dt of x of t. Differentiation property. Time differentiation property is s into x of s minus x of 0. S into x of s minus x of 0. Now, general formula, Laplace transform formula. What is the Laplace transform of a signal x of t? The Laplace transform of a signal x of t is equal to x of s is equal to integral minus infinite plus infinite, right? X of t into e to the power minus st dt. But here our x of t is 0 for t less than 0, therefore lower limit is 0 to infinite, not minus infinite to plus infinite. Okay, this is 0 to infinity. So as per the formula, we are writing now Laplace of d by dt of x of t. Laplace transform of d by dt of x of t. So what happens? Integral 0 to infinite d by dt of x of t into e power minus st dt. So this is the Laplace of d by dt of x of t. So d by dt of x of t is here into e power minus st dt. Okay. Now, in the place of LHS, Laplace transform of d by dt of x of t, we know this is s into x of s minus x of 0. So that I am going to write s into x of s minus x of 0 is equal to integral 0 to infinite e by dt of x of t into e power minus st dt. Okay. Now on both sides we are going to apply limit s tends to 0. So in the final value theorem it is there, that is why we are applying limit s tends to 0 on both sides. So apply limit s tends to 0 both sides. Then we can have answer. So limit left side limit s tends to 0 s into x of s minus x of 0. So on right side also same limit s tends to 0 and integral 0 to infinite d by dt of x of t into e power minus st dt. So if you apply limit s tends to 0, so e power minus 0, it will become 1. It will become 1. Then left side we have limit s tends to 0 s into x of s minus x of 0. Here the limit is not applicable for x of 0 because there is no s term. So right side what happens? After applying limit you get integral 0 to infinite d by dt of x of t dt. So here integration differentiation in same domain. So integration and differentiation cancelled. So what is remained? X of t is remained and the limits are 0 to infinity. So substitute upper and lower limits. So upper limit is x of infinity, lower limit is 0. So x of 0 minus x of 0. And what we have left side, limit s tends to 0 s into x of s minus x of 0. So both sides we can do this minus x of 0 cancel. Then we have x of infinity is equal limit s tends to 0 s into x of s, s into x of s. This is the final value theorem or final value of the signal. Here x of infinity means final value of x of t or signal. Okay, so the final value we can do by using this limit formula. Limit s tends to 0 s into x of s. So very easy, simple. Okay, so we can do problems in the next session. So thank you students. Watch videos regularly. Thank you.